Hi everyone, this video is on exercise 12i question 3. So we want to find the coordinates of the points where the gradient is 0. This basically means find the stationary points, and we also want to establish whether these points are local maximum, local minimum, or points of inflection. Okay, so in order to find the stationary points, we need to differentiate the function and then set the derivative equation equal to 0, and the solutions to that equation are going to give us the x coordinates of the points of the stationary points. And once we have the x coordinates, then we can use the x coordinates to find the y coordinate. So let's do that first. Then I will explain how we can find the nature of these points. So divide by dx is equal to 8x plus 6, and setting this equal to 0 is 8x is minus 6, which means x is minus 6 over 8. So this is the x coordinate. This point has only has one stationary point, and its x coordinate is minus 6 over 8. So to find the y coordinate, we basically substitute that into the equation of the of this curve, which is y is equal to 4x squared plus 6x. So when x is minus 6 over 8, then its y coordinate is equal to minus 9 over 4. So the stationary points of this curve has this coordinates. So these are the coordinates of that. Okay, so now that we have the coordinates of the stationary points, we need to establish whether these are local maximum, minimum, or points of inflection. So in order to determine the behavior, the nature of a stationary point, we need to find a second derivative first, and by considering the value of the second derivative, we can then determine whether it's a minimum, maximum, or a point of inflection. So it's worth mentioning that whenever we have a specific x coordinate, we substitute that into the equation of the second derivative, and if that's positive, then that means the point is a local minimum. If it's negative, then the point is a local maximum. And if it's 0, then it could be a local minimum, local maximum, or point of inflection. We need to check the behavior on either side. But this is just an explanation. Let's see how can we use that in practice. So in this case, we first find the second derivative, d squared y dx squared is equal to simply 8. Now here, this example is an exception in a way, because your second derivative is a constant function which is always positive. So this simply means that basically the coordinates of the stationary point that we had, minus 3 over 4, minus 9 over 4, is a minimum, basically. So is a minimum point. Yeah, but there are many cases that your second derivative is not a constant function. Let's say it's 2x, and in those cases we can substitute the x coordinate of the stationary point and see what is the value, if it's positive, negative, or 0. Then depending on that, we can decide the nature of the curve, a stationary point. Right, now let's do part B. So y is equal to 9 plus x minus x squared. Again, we first find the first derivative, so we get minus 2x, 1 minus 2x. Then we set this equal to 0, so 1 minus 2x is equal to 0, which means x is a half. So here a half is the x coordinate of the stationary point, and we find the y coordinate. So when x is equal to a half, then y is equal to 37 over 4. So the coordinates of the stationary point are half and 37 over 4. So this question is very similar to the previous one. Okay, now in order to determine its nature, we need to find a second derivative. So d squared y dx squared is equal to minus 2. So once again, we got another constant function, and again, this second derivative is always negative. so we don't even need the substitution part. But in the next examples I'm going to show you the other case. So yeah, because of that, since the second derivative is less than 0, we can conclude that this stationary point is a maximum point. Right, now let's do part C. So we have this cubic function. Let's find its derivative. So we get 3x squared minus 2x minus 1. And now we are going to set this equal to 0. So this time, it seems like we are going to have more than one stationary point. So divide by dx is equal to 0, which means 3x squared minus 2x minus 1 is equal to 0. And we can solve this quadratic. And when we solve this quadratic, there are two solutions. So x is minus a third, or x is equal to 1. Now we need to find the y coordinate for each of these points, which means we are going to have two different stationary points. And then we can determine the nature of each of the stationary points. So when x is minus a third, what happens is that the y coordinate is equal to 32 over 27. So one of the stationary points is minus a third, and then 32 over 27. So for the other point, when x is equal to 1, then the y coordinate is simply equal to 0. So another stationary point is just 1 and 0. Right, now it's the time to find the second derivative. So d squared y by dx squared is equal to, so this is the equation of the first derivative. So differentiating that gives us 6x minus 2. And this is the case that I was mentioning earlier, because most of the times we don't get a constant function for the second derivative, but things like this sort of things that we have 6x minus 2, or anything, it could be a quadratic, whatever function it is, but it's not constant. So in this case, in order to determine the nature of each of these points, we need to separately substitute the x coordinates of each of the stationary points, and then see what are the signs of the second derivative. So let's start with minus a third. So then ds squared y by dx squared is equal to, when we substitute that into 6x minus, we get minus 4, which is less than 0. So this means this point is a maximum. So we can conclude that minus a third, 32 over 27, is a maximum point. And the next point is when x is equal to minus 1. Sorry, it's positive 1. Then in that case, d squared y by dx squared is just equal to 4. And this is positive, so therefore this point, the point 1, 0, is a minimum point. And yeah, this is how you can determine the nature of the points in most of the questions, because normally you need some substitution. But yeah, there are other cases that I'm going to do in the next few videos. All right, that's it for this video. Thank you for watching.